So real quick, we're going to talk about the difference between GPU and CPU. Most of you probably know that. I'm going to do a very brief comparison between OpenCL and CUDA. There's going to be a lot of people. On Friday, you're probably going to get 4 hours of this guy. I'm just going to give you, this is primarily just so that you realize these two things exist, and you're going to have to pick one or the other. They are the frameworks to code on GPUs. That being said, the abstractness of OpenCL is kind of helpful for this talk, so I picked the OpenCL framework just to give you an idea of how GPUs work, but you could have easily picked CUDA. I'll give you a really quick description of GPU hardware, because it's actually very important to understand what's going on chip so that you plan your algorithms accordingly. This is where we're going to probably subtract the time, but I have a lot of coding obstacles that basically the whole point of these 5 points is before you even spend the massive man hours that you want to code something in GPUs, if you're not aware of these things and your algorithm cannot take them, there might be no point at all, right? Because these are hardware-specific and language-specific issues, and we'll try to go through them in turn. And then I will end with the n-body example of hack, because Hal and Salman did a good job explaining what that code does, so you guys don't need too much review on that. So this is a dated slide, but I'm just here to show you that these are indeed architecturally different devices. That's all this slide is meant to show you. This is extremely, in fact, even in 2010, it's a pretty dated slide. So let's go right into it. What is a CPU, right? CPU typically follows what we call the multi-core design of a microprocessor, right? And it's an attempt to increase the speed of sequential programs, right? And there's a lot of nitty-gritty great things that go into CPUs that allow you to run sequential programs extremely fast, right? Out-of-order execution, branch prediction, a bunch of other stuff that you've heard probably a lot of or will hear a lot of this week. We've now in a generation of adding multiple cores, right? Which now allows us to get in the regime of multitasking these sequential programs, as well as threading, but not the kind of GPU threading I'd like you to get used to. So this is the last time I'm going to use threading and CPU in the same sentence, because this is probably the last slide you're going to see about something about a CPU. But this is something we all know, right? This is a CPU. A GPU, on the other hand, follows the many-core design, right? So multi-core, many-core, right? Obviously, remember, if you recall in that last picture, we had 4 giant cores. Here are the GPU cores. And I think you had a NVIDIA talk earlier, so you've seen this, right? This is on-chip. These are thousands of cores ready to go. This is the L2 cache, et cetera, right? The point of a GPU, though, is it's to maximize throughput of parallel algorithms. Recall with CPU, I said serial algorithms, right? This is parallel algorithms. The whole point of this beast is to take your problem, break up into a bunch of tiny little pieces, and get high throughput of it. And I'll give you an analogy for this in just a second, but this is just to get our feet wet, right? Throughput of single precision, as Hal said, has increased dramatically. This is the plot everybody loves to show, and I'm sure the NVIDIA guy showed it, right? This is the single precision flop rate compared to CPUs. This is a little bit dated. This is August 2012, but you can clearly see that if, in theory, you got the GPU to run optimal, you can get a massive boost in flop precision. And notice, by the way, that I think, as Hal said, it is a factor of 3 difference between single precision and double precision, right? Or even, if at all possible, to reduce the precision on what your kernel is, your workload, is extremely beneficial, especially if you want to make use of this curve, right? However, this curve is extremely misleading for the following point that many algorithms are very not well suited for GPUs. And we're going to get into this, but I don't like when people show you this curve and say, clearly, the future is heterogeneous programming, and this is why, and all code should do this, right? It's not true, right? There's a lot of applications that just are not well suited for GPUs, and a lot of CUDA guys and a lot of NVIDIA work has gone into shortening that list, but that list still exists. And the whole point of this talk is to give you ideas of things you should think about before even trying to achieve this flop rate, right? Any questions so far? This is all pretty straightforward stuff, right? So I have a question for you then. Would you rather outsource a project, right, your science or whatever, because you might need to do this, to a capable contractor or a graduate student? It's OK. You can laugh. It's fine. I hear he's a nice guy. And so the point about the capable contractor is this guy's probably going to give you low latency and good throughput, right? This guy's going to work quite a bit of time and get a pretty good throughput coming out. And depending on whether it's before or after 5 o'clock, this guy's probably going to have high latency and low throughput, right? So you'd be like, oh, well, obvious choice, right? The capable contractor. OK. But what about many more graduate students? Oh. They're all productive in some fashion, right? That guy's really productive. I know him pretty well. Right? So now you got all these guys working for you. You've got this workforce, right? And all of a sudden, your problem has changed, right? You have this low latency, good throughput. But you also now, by gaining a bunch of graduate students, have achieved OK latency, but very high throughput. And this is kind of the comparison to a CPU GPU, right? This guy is going to, because he doesn't have branch prediction, because he doesn't have all these great things, you're going to be hit with latency operations, right? But because you have so many cores working with you, right, you can get high throughput versus the CPU, who's going to have extremely low latency, comparatively speaking, but reasonable throughput in comparison to the massive number of cores in the GPU. So that's just an analogy I like to use to get you thinking about how these things work. One of the biggest problems, though, that the first question I would say whenever somebody asks me, should I port my code to GPU? The first statement I should say is, do not forget Amdahl's law. You've probably seen this curve, but I'm going to show it again. And there it is. All this curve tells you is if you have a process and you divvy up that process over n processors, how much of the speed up can you achieve, right? And this is a very simple function. All it basically tells you is that, let's say you profile your code and you say, 50% of my code must be serial, must be executed sequentially. And the other 50% of my code can be broken up into pieces. This law tells you, yeah, you're only going to get a factor of 2 increase in speed. So you might think, oh, wait, half my code could be accelerated. Let's do this. Let's spend the work hours and put this in here. And frankly, this might not be worth it. And this is the power of 2 Salman keeps talking about, right? This is a big problem. And it turns out the only real gain is, let's say your parallel portion is 95% or your serial fraction is 0.05, which 1 over 0.05 gives you 20%. You could actually get a 20 times increase if your code has a very small serial fraction portion. So the first thing I would say is profile your code, which you should have already done anyway. And if your algorithm just does not allow for something that, it does not allow for a small serial fraction, you're already kind of wasting your time. And really, the only way to get use of this quickly is if you use something like OpenACC, which we can talk about later if you guys have any questions about that. So restated, takeaway, you're completely limited by the serial fraction. So like I said, if your code has a large serial fraction, there's no point in accelerating GPUs because you're not going to get anything for your time. OK, so now let's say you've done the profiling. You've restructured your algorithm. You're like, OK, I think I actually could break this up into tiny pieces and accelerate on a GPU. Well, the first question then you're going to hit is, well, wait, should I code this in OpenCL or CUDA, right? And for those of you who don't know, CUDA is a NVIDIA vendor-dependent language, right? And there's pros and cons to using either of these. This is one of the biggest cons for CUDA, right? You can only code on NVIDIA GPUs. Contrary to what you might believe, they're not the only GPU manufacturer, right? There is AMD ATI, right? That's the first problem you run into. However, CUDA is extremely more mature than OpenCL in this sense, meaning you're going to have a better chance of finding highly optimized libraries, right? So if you're coding and you're like, oh, I need to do a matrix inversion, do all these other things that you would think would be common practice, chances are there's a library that's already been created and optimized for CUDA NVIDIA GPUs for the specific card you're working on, if it indeed is a NVIDIA card. OpenCL, on the other, so any questions about that stuff? OpenCL, on the other hand, is a very interesting abstract language. It can run on many different heterogeneous platforms, not just GPUs, right? GPUs, CPUs, DSPs, et cetera, right? And so the cool thing about that is that hypothetically, you could then start being able to test the waters of having code that's portable to other machines. And once again, though, since each chip is different, you're going to have to optimize your kernel for each chip. The only thing that you fix is that you're doing it in the same language. Another a con to OpenCL is because it's lower level language, it's harder to code just because it's more abstract. It doesn't a priori know what device it's going to be run on, and you will see that as I go into the framework models for how this is run. So basically, to sum all that up, CUDA is vendor dependent but extremely mature. OpenCL, you have a lot of freedom but harder to code, and you might not have access to these libraries. Which to choose completely depends on what you want to do, what platforms you want to use, and the targeted users. And of course, this is another one of those things where I hate when people make a statement like this and not give an example. So let's just say you have a code that you want to download from the internet, and you have no idea what the person's laptop is going to have on it. You don't even know if it's going to have a GPU on it. I mean, these days it probably will, but you don't know. OpenCL might be the way to go, because it can query whatever device it's on, figure out which devices it has attached to it, and then launch appropriate kernels that you've written. CUDA can't do that. On the other side, let's say you're running on a cluster that you know for sure is accelerated by NVIDIA GPUs. CUDA might be the way to go. It might be easier for you. It will be easier for you to code it because it has the assumption that it's coding on GPUs and is not as lower level as OpenCL is. But on the flip side, you don't gain as much on portability, right? So these are all questions that is very application specific, but it's important for you to be aware of what's going on. That being said, because OpenCL is lower level, ergo more abstract, I'm going to use their platform model to explain what I want to get by on this talk. So OpenCL, like I said, does not know what device it's hooked up to. I mean, I put parentheses GPU, but this could be anything. So OpenCL treats things in two platform models. It basically says there's going to be two codes, what we call the host code and what we call the kernel code or the device code. It doesn't know if that kernel code is going to be launched on a DSP or a GPU, but that is what you're telling it, right? I'm going to code this host code. I'm going to code the kernel that will be launched on the device. The host code's properties are basically, it needs to be able to query which devices it's on to determine which kernels to launch. It needs to do the push and pull to the device. It needs to be able to tell the device, do this problem, and here's the memory you need to do it. And it typically performs all of the complex logic of your application. So like I said before, the GPU cores, there's many of them, but they're relatively dumb, right? They're the graduate students of chips, right? So the problem is that you cannot have branch logic. And as Hal had mentioned, if statements and for loops become extremely worse, actually, if you look at GPUs, and we're going to get into the specifics. But the point is that this host code, which lives on the CPU, right, is the driver of what launches devices, will have all the complex logic. And it's the host code's job to farm out its very computationally heavy but relativistically, algorithmically simple tasks, oh, try saying that, to a GPU, right? So basically, it's going to say, I need to multiply these two arrays. I need to do it 1,000,000 times. The GPU is like, yeah, I can do that. Just tell me what to do and give me the memory. A very key note is, notice this says push and pull memory to and from device. The kernel code has no access to CPU memory. This is an important point, and we're going to get back to it. This is an example of a kernel I just put up there, just so you guys get an idea of what it is. All I'm doing is telling the GPU, in this case, I'm sending you a global, which we'll get into what this means. I'm sending you 3 arrays. I want you to do this operation. Very simple thing I'm doing here. Unfortunately, this thing got cut off. You should see curly braces, right? But very simple. This is ideal for something like a GPU. This can throughput so hardcore on some sort of algorithm like this, right? Unfortunately, what I've done here with global IDs is actually not very good, and we're going to go into why that is. So like I said, you have your host code and you've got your device code. The host code will launch kernels on your device. But there must be some sort of structure to this kernel execution. And this is what it is. Each kernel launch is called a work item. Some people would call these threads. Then these work items can be collected into what we call work groups, and work groups are a part of the whole global system. So all this is saying is, at some point, let's say you don't want to just add 2 arrays, but you actually want to perform a more complex problem. You need some way to attack this problem. You need some way to attack complicated logic of some sort. And all this is saying is that I can run a kernel which fits in this global network of other kernels. And based on its group, local, and global ID, I can be extremely specific on what I want that specific kernel to do. And I can be extremely abstract by saying what I want the global kernel to do. So basically, this is a very complicated slide, actually. But all this is saying is that given a kernel launch, I need to launch these kernels on all of the threads of my GPU. This is how you determine which one is unique. And this is how you do the more complex logic. And we'll see an example of this. Last thing I want to talk about in the OpenCL is just the OpenCL memory hierarchy. All this says is that, so the OpenCL has this host code. It launches these kernels. These kernels are executed on the threads of the GPU. That's pretty straightforward. But what memory do those threads have access to? And this is how OpenCL divides up the memory. It basically says there's going to be some global memory, which is going to be around, for a GPU, around 8 gigabytes if you're like a Kepler, which every thread has access to, meaning no matter what kernel is being launched, each thread will have access to this global memory. But the latency is high, and we're going to get to that. There's constant memory, which is identical to global memory, except for it's read-only, and a lot faster to fetch. There's local memory. So remember I said threads can be collected in groups. A local memory is the memory that a group can see specific. So it's a group-specific memory, meaning if you're in a certain group and you cache something in local memory, everybody in your group can see it. But everybody in another group can't see it. And then there's private memory, which is registries, meaning what memory does the thread have itself. The last bit of memory hierarchy is the host side. That's the CPU side, and that's everything we know so far. That's just, basically, in fact, if you look at a supercomputer like Titan, that's where most of your memory is going to be. And I'll get into that in just a minute. But this is just how OpenCL treats its memory hierarchy. OK, and here's a diagram just to make it clear. Here's your CPU. Here's most of your data. You push that data to the GPU. This is the GPU's global memory. This global memory has access to all of the work items, or threads, as I've been calling them, right? These guys can all see this. And then these threads are grouped in what we call work groups. There's, in this case, M of them. And these work groups have their own local memory. And each thread has its own private memory. So we're going to get into what this actually physically represents, but this would actually a work item from a GPU standpoint, because recall, still I haven't mentioned a real device yet. This is still OpenCL abstract talk, but really if you're running on a GPU, work item is one-to-one correspondence with a core, one of those little cores. This is what a Kepler looks like. This is the L2 cache of the Kepler, right? This is the global memory. And that makes sense, right? All of these threads, these are the work items, just as he was asking, can have access to this giant cache of global memory. Here's the, I think this is on this diagram, the local memory, right? So mapping terminology, work item corresponds to the one green dot. Work group corresponds to one SM. And then all of them are on this chip. So I had global, local, which corresponds to here. And remember, local corresponds to a group, which one of these is a group. And then you have the private registries, which are all over the place. But that has the private memory of your data. Fine. Let's zoom in a little bit. Right? Work item, notice there's the registry, and there's the local memory that only this group can see. It's a physical thing, right? What I mean by only this group can see is it's only on this chip. There is no access to, the only way you can cross local memory is to go back to global memory and then fetch again on another group. Remember I said OpenCL launches kernels, and it divides them into items, groups, and then the global network. The actual hardware does not launch these, doesn't just say, great, launch all of these threads. What if the thread number, what if all those little cores does not equal the number of kernels I need to launch? What if the number of groups does not equal the number of cards I just showed, right? There was 15 cards. What if I needed 20 groups? What it does is it has an execution model. And all that simply says is that each group is launched on each one of these SM cards, and it launches 32 threads at a time. And they're all performing what we call SIMT operations, single instruction, multiple thread. So what that means is that those threads are all launching the exact same calculation. And you might say, wait, that's weird. What if certain threads within that 32 need to do different things? That is a problem, and I will show you how to get around that if you can. And so all this is saying is the way the GPU actually runs when you execute an OpenCL code is it says, what are your groups? I will launch as many of those groups as I can on as many cards as I can. I'll execute them in 32 thread launches. And I will do that until I run out of tasks you have given me. So one launch might not finish your problem, but it will continually run until it outputs. And you can imagine, if this number is not modulo your thread number, and if the group size is not modulo the number of things you can fit on this card, then it has to do some spiffy things. But that's stuff you don't have to worry about, and it hits you with performance. So the rule of thumb is you want your group size to be modulo 32 because you want them to run these cards. You don't want your memory to be too big because if the memory can't fit on the SM card, it will actually crash. I think the new Keplers will actually push it to global memory, which is actually almost as bad as crashing. And that's basically all the stuff I wanted to get by. Where we're at now is basically we have a GPU. It executes these kernels. These kernels are executed specifically on this hardware, and this is how they're done. And I give this table mostly for reference. I'm not going through it. But this is a Kepler schematic, and this just shows you just how many threads I'm talking about, right? I mean, look at the number of registers. Look at the number max threads per block, and you get 8 blocks. This is a lot of threads. You get a lot of throughput. Work item corresponds to this. Warp corresponds to launching 32 of these simultaneously. Group corresponds to running a group on this card. It can launch multiple groups on this card, but a group cannot exceed the size of this card, or bad things happen. And global memory is that giant cache that I just, there, that guy. OK, quick GPU stumbling points that are very important to consider. And this is the meat of the talk that I want to get by. And these are things you should be aware of before, once again, you start coding on a GPU. Because if you find these things out later and realize that your code cannot account for them, your performance hits are going to be humongous. The first problem is GPU storage of memory. You don't have a lot of memory. And as I've written here, maybe on a Kepler you get 8 GBs. So for example, this is a problem at Titan, because if you don't have a lot of global memory, that means that you can't let all of your data rest on the GPU, which basically means I can't just do, most likely, I can't do one giant push of data and then tell the GPU crank away and give me the answer. It won't fit all my data. This is all I want to get by with this slide. Do you have a shortage of memory? Lockstep execution, all this is exactly the same as SIMT. All this means is, like I said, 32 threads will be launched, and they are all running the same instructions. So what if I have a statement like this? If my thread ID is less than 4, do something else, do something else. What this is saying is if I'm thread number 0 through 3, I want to do this task. Otherwise, do this task. but it's going to launch the first 32 threads, and it hits this. It will launch this, and it will calculate this entire if statement, pause, calculate this entire instance if statement, pause, figure out who needed to know what, and continue. You can imagine how bad that is. This is not how a CPU does these things, right? This is actually performing both if statements. You might as well have just calculated them both there anyway, right? This is a very bad problem. This is called lockstep execution, and there are two solutions. First one, don't do it. That's a pretty easy thing for me to say, right? You can just be like, don't do that, right? I didn't add another solution here, arithmetic ifs. Do you know those kind of ifs where you perform the calculation on all of them, but then if your thread ID is modulo 4, it becomes a 0, otherwise it's a 1. And so you can do arithmetic if statements if you can. But basically, the point to this is if you're going to have if statements, they better either be modulo 32, or they better be a very small part of the code and not affect your performance. But this is a humongous latency hit. And this is something you all should be aware of. Memory latency. This goes back to somebody had a question here. Global memory is the worst latency hit you can have. Basically saying, if I have a thread and I say, I need an element from global memory, that is hundreds of cycles latency to do a couple cycle computation. Hundreds of cycles to do latency, doing nothing to perform a few cycle computation. That's a problem. Local memory, the one that's on chip, much faster, but can get bank conflicts, and I'll describe them in a minute. And so basically, the solution to this latency is you probably want your groups to copy most of its memory from global memory to local memory and have the group's threads actually use the local memory as much as possible. Now, you might say, but wait a minute, the local memory is probably a lot smaller than the global memory. This is true. But recall, your problem has been diagnosed into tiny pieces. So if your group has just 32, let's say, tiny pieces, then those 32 tiny pieces might not need a lot of data. So cache that into local memory and access it there. And I'll show an example of that. And this is an example of doing something wrong. Notice how I'm accessing global memory. This is global, global, global. This kernel, which looks like it should be super fast, is extremely slow because I'm not caching in local memory. And that's what I was saying earlier. One way around this is coalesce memory transfers, which is kind of true no matter what you do. Even if you work on CPUs, this helps a lot. But basically, all this is saying is if I'm going to fetch from global memory, which I have to do because that's the 8 gigabytes, right? Local memory is small. So I'm going to have to grab stuff from global memory anyway. If the threads grab it sequentially, it can do coalesce fetches, send them in bigger chunks. So if I do this, for example, if I want to get this guy, and then maybe this guy, and then this guy, and then maybe this guy, and this guy, the actual GPU hardware is going to perform these sequentially. So here's 100 latencies, here's 100 latencies, here's 100 latency, here's 100 latency. That's bad. So if the best thing you can possibly do is to access your memory sequentially, and that's the big key of this slide. Newly allowed by Kepler, which is very nice. They don't even have to be accessed in order. It used to be thread 0 should access something, thread 1 should access the next one. It actually turns out you can muck around all over the place just as long as the total memory access is sequential. That's all that slide's telling you. And that can be very handy. It opens up doors for new applications. The last slide before I show an example is there does exist a visual profiler. This actually does exist. It's not super trivial to use, but it's pretty straightforward. And the kind of information that gets spit out by these profilers are actually hardware specific. And I can't get into them, but basically, you worry about things like occupancy. It's extremely important. And all I want to get across with this slide is a profiler does exist. So you can actually keep track of how you're doing. You don't have to just read my slides or NVIDIA slides and then try to do that, get a number and say, how am I doing? There is actually a profiler that tells you, by the way, you have this many divergent if statements. This is why it's taking me long. By the way, you have this many global memory fetches. This is why this is taking me this long, right? And that's basically what that's for. So very quickly, within my last 5 minutes or so, I'm going to give an exemplar, which is our hack code. As Salman and Hal has said, it's an n-body code, which resolves force, right? It's just a force calculation. You have particles, and you want to resolve the force on those particles. When you run just the PM solver, which is the FFT code, which is super fast, it gets everything right up to the short range, which for all intents and purposes of this talk, we'll call it 3 grid units. Meaning, if I decompose my box into a grid, and I take a particle anywhere in that box, and I draw a circle of 3 grid units around it, all the particles within that circle will have been miscalculated by the PM code. So to increase resolution, you can either use a tree algorithm, which we all heard a lot about, so I don't have to talk about it, or you can do the naive brute force, which just says, given this particle drawing a circle of 3 grid units, do a direct n² calculation of all the particles within that grid of 3 units, that circle of radius 3 units, right? And it turns out we have a GPU version of the brute force method because the algorithm is simpler, ergo easier to code on GPUs. And it's a factor of 2 faster than the tree code at scale. Right? So doing the way more computationally heavy problem, accelerate on GPUs at scale for the same problem, we actually still have a factor of 2. I think here we say 4 or 5. There's really, it depends on what we mean. And to be a fair comparison, I'm already being unfair because I'm testing completely different algorithms. But what I'm just saying is that you can get a lot of throughput if your algorithm allows you to do that. Great. So here's my video. So you imagine a cube of data, right? Salman showed you a very cool picture. This is on one core, or one node, I should say. And you divide that data into slabs. So you have a bunch of particle data in here. And all I'm saying is index that particle data by slabs. Right? If you're in here, if your particle lies here, you're in this slab. If your particle lies here, you're in this slab. Pretty straightforward. Make your slab width 3 grid units. Why am I doing this? The reason I'm doing this is because if a particle lives here, the only particles it needs to see to perform the correct short-range force calculation is the particles in this slab and this slab, right? A particle here does not need to see a particle here because we know the PM solver has already done that correctly. It's done the long-range force correctly. We're just trying to do the short-range force. This is why I index my grid like this. OK, so now imagine a GPU. And what I'm going to do with the GPU is I'm going to push these slabs into the GPU one at a time. Remember, I said the GPU is memory bound. So I can't push the entire cube. But what I can do is I can push a couple slabs and have it calculate away. And that's what I'm doing here. I push in, let's say, the first 2 slabs, because like I said, this slab only needs to see this slab. The GPU takes those 2 slabs. To update this slab, it just needs to calculate particles from this slab. Simultaneously, I can send in a 3rd slab. And while the middle slab is being calculated, it has all it needs, because all it needs to see is the guy to the left and the guy to the right, because recall, these are spaced by 3 grid units. Does that make sense why we're doing the correct short-range force updation? This slab only needs to see the particles to the left and to the right of it. What's nice about this is I can asynchronously push these slabs in while I'm calculating away. This saves us because it's the PCI bus to push data from the host code to the GPU code is also a heavy latency hit. So we actually can synchronize pushing slabs to the GPU while simultaneously calculating on the previous slabs. And if you notice from this diagram, all I need to have is memory for 4 slabs, which it turns out in our application we do. But what do I mean by updating the particles, you might have asked. And so let's zoom in on one of these slabs and let me get an idea of what's going on. So let's take these guys away. And I lied, actually, when I said I decomposed this cube into slabs. I actually decomposed them into what we call chaining mesh shells or just little grid boxes. And what are the dimensions of this grid, you might ask? The best guess would probably be 3 by 3 by 3. Why? Because the particles in this little box technically only need to see this box, and the boxes around it. Right? Why do I do that? Now if I push in, let's go back to the 3 slab case. And we are, let's see here, updating this guy. All this guy needs to see is himself, these neighbors on the bottom, and the neighbors on the top. Does that make sense? To update the particles that lie in this domain, he just needs those neighbors. Notice how I've taken a giant problem and I've decomposed it into these tiny little squares. Ideal for GPU. And this process continues. So now let me start going back to using these terms that you all have probably forgotten. This would be our work group. The particles in that cube would be our work items. And the memory I cache into local memory would be all of its neighbors. And this is what I mean when I highlight the slab green and I highlight the 2 adjacent slabs yellow. The last slide is basically once again, you push this data in and you update your cube. And you do that for the entire cube. What I would like to end with is an optimization checklist. So these are the things I very quickly said in the talk, but we can check them off to make sure that I'm actually doing them. Memory storage. Like I said, the GPU does not have a lot of memory. So how do I overcome that? I use slabs. Check. I don't have to send the whole cube. I just need to send slabs. Lockstep execution. I didn't say this in the previous movie, but excuse me. I don't need if statements, right? Because I made that cube the size of the group, right? I said the group is those little cubes. all the particles within that little cube are doing the exact same thing. Calculate the short-range force of all of the neighboring cubes. So there's no if statements in my kernel. It just says, given this group, do an n-squared computation of all these particles surrounding me. So there's no divergent if statements basically saying I don't have this lockstep execution. This is what my solution of don't do ifs is. If I broke down my problem so that into a small enough piece where the groups don't have to do divergent logic. Global memory latency, that's a quick fix. Like I said, you can't grab global memory. I mean, you don't want to grab global memory sparsely. But I don't care about what order I grab the particles in. I only care about their locality. So if I arrange my array in just the way I visually portrayed it with these cubes, then once one thread asks for one particle in the array, all of the other threads need adjacent particles because my array, my domain has been partitioned into these little cubes, right? That's a fancy way of just saying I can go to memory and fetch sequentially. That's all that's saying. Coalesced memory fetching is what all that means. And then I didn't talk about bank conflicts, but I avoid them. So the conclusion that I'd like to pull up is that GPU accelerated gains are completely determined by the serial fraction. We forgot my Amdahl's law curve already, but all this was saying is step one, what part of your code can you break up into small pieces? And if that part is not large, don't do GPUs. That's the first thing I wanted to get by. OpenCL allows one to use any heterogeneous platform versus CUDA, which is more mature but vendor specific. All this is, like I said, you could use this for a bunch of different platforms. You can use this to make your life a little bit easier if you know you're using NVIDIA GPUs. Here are the GPU-specific considerations: low memory storage, lockstep execution. The threads concurrently run the same instruction. It takes a long time to fetch from global memory. The way you overcome that is you sequentially fetch from memory, and I didn't talk about bank conflicts. And there does exist a profiler to help you determine what your performance is actually doing. And I'll take any questions now, and there's my email in case you guys have further questions.